Good morning, everyone. We shall continue the problem what we were discussing in the previous classes. Uh, in the previous classes, what we have done was we had calculated the dimensions of the foundation, length, breadth, and depth. So the overall depth of the foundation was found to be after calculating the bending moments diagrams and checking for punching shears. We have obtained at a value of overall depth d, which is equal to 660 mm, and the effective depth small d is 592 mm. I believe at this point of time you will understand overall depth and effective depth and all. Okay. Continuing with that, we have to find the reinforcements. What are all the types of reinforcement that we will encounter? We shall see today. And basically, what we have is two types of reinforcement. One is along the length of the foundation, which is called as longitudinal reinforcement, and another one is along the transverse direction, transverse reinforcements. One more important type of reinforcement what we will encounter is a shear reinforcement. So to counteract the shear forces, we have to provide some reinforcements. So these are all the some basic types of reinforcement where your foundation is required. Since we are doing a slab type foundation design, that is combined rectangular footing, uh, in this problem we shall first start with the design of longitudinal reinforcement. As you all know, when we have moment value, that means bending moment, we can easily calculate the steel required, that is AST, area of steel. Uh, to calculate the area of steel in the longitudinal direction, we shall consider the reinforcement at center span or center span, or we shall also say under maximum bending moment. So hogging bending moment anta kuda kariತಾರೆ. Here what we have is we have mx is equal to 510 kilonewton meter. What is this 510 kilonewton meter? We shall observe here. In this bending moment diagram, you can observe that this is the maximum bending moment, which is 510 kilonewton meter. Here you can observe the 510 kilonewton meter. So this is the we have to find the longitudinal reinforcement for this moment, as well as in the next step we will be doing the longitudinal reinforcement under column A, and then we will be doing the longitudinal reinforcement under column B. So this is column A ಬರುತ್ತೆ ಇಲ್ಲಿ, column B ಈ ಕಡೆ ಬರುತ್ತೆ. So this is maximum bending moment. So we shall consider this section as XX. So we shall consider this as section XX. So the bending moment what we have here is mx. Okay. So first we shall consider this moment and shall calculate the reinforcement. Second, we shall consider this moment value and calculate the reinforcement. And next we shall calculate this one. Okay. So let us start with the session. Continue the problem. So I'm first considering this problem. We have consider mx, that is mx is equal to 510 kilonewton meter. Whenever we are substituting the moment value in a limit state formulas, that is from IS 456 2000, if you have the code book handy, you can refer to IS 456 2000. I have given the clause number G 1.1b. So we have this formula, which is mu is equal to 0.87 FIAST into du multiplied by 1 minus FIAST by FCKBD. So this is the formula what we have. Maybe BD square ಇರ್ಬೋದು ಇದು. Formula correct ನೋಡಿ. mx is what we have. So whenever we need to substitute the moment value in limit state formulas, equations. So we have to consider the ultimate moments, that is factored moment. Factored moment ಅಂತಂದ್ರೆ what we have to do is we have to multiply the value by 1.5. So we have to multiply the value by 1.5. The moment value is 765 kilonewton meter. Since Fi and Fck are all in Newton per mm square unit, we have to convert this moment value to Newton mm unit. So 765 into 10 power 6 Newton mm. So we have this conversion. Okay. So for easy substitution, if you have latest calculator, white calculator, you can calculate the AST by substituting the values directly by keeping the AST unknown. If you don't have that, if you are using an older calculator, so to ease the calculation, we have modified AST equation. So you can observe here we have this modified AST equation. You shall note down this one. So you should note down this one. AST is equal to 0.5 FCK BD divided by Fy multiplied by 1 minus under root 1 minus 4.6 M, which we can also call this as MU divided by FCK BD square. So this is the formula what we have. So I'll substitute the values. 0.5 FCK M20 concrete is given in the question. So I'm using 20 Fe415 steel, so 415. Substitute the values. 4.6 M is 765 into 10 power 6 divided by again FCK is 20, B which is the width of the foundation 1800. Here depth D, small d, here you should be very careful here. This D is effective depth, not the overall depth. Overall depth is 660, so the effective depth is small d, 592, which is 68 mm lesser than 660. This is how you should substitute. Here this value is 1800, which is the width B, and the D value we have 592 again. We should substitute. So after substitution, what you'll get is AST is equal to 3872.96 mm square. So here for considering the values of see, we have one thumb rule for selecting the dimension of the bar. So you may be confused that about what kind of or what should be the diameter of the bars which we should be selecting at. See, basically, we have a thumb rule. Usually, what we do is if the AST is less than 1000, so we will go for the bars which is lesser than 10 mm. So if we have the AST value in between 1000 and 2000, we will go for 12 mm, 16 mm, 20 mm like that. So if we have AST value greater than 2000 mm square, we will go for 20 mm, 25 mm like that. So about 20 mm diameter. If we have more than 3000, 4000, likewise, so if we have more than 3000, we shall go for 25 to 30 or 35 according to the requirement, and spacing requirements also we shall consider. So here to illustrate that I have just taken 16 mm dia, whereas according to the thumb rule I should be taking 30 mm or 25 mm dia bars. So I'm just taking 16 mm dia bars. What will happen is the spacing of the bars will decrease. So illustrate that I have taken this spacing is equal to spacing. We have common formula, area of one bar divided by area required, that is AST, multiplied by width of the foundation. Width of the foundation in our case is 1800. So that is what I have substituted here. Uh, 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 See, we have area of one bar. So since we have considered 16 mm dia, pi d square by 4 divided by actual AST multiplied by B. So I will get the value as 93.44 mm. So the fines, always you have to consider the lesser value what you have, say 90 mm. ಡೆಪ್ತಿಗೆಲ್ಲ ಏನು ಮಾಡ್ತಾ ಇದ್ವಿ 93 ಬಂದರೆ ಸೇ 100 mm ಅಂತ ಅಂದ್ಕೊಳ್ತಿದ್ವಿ. ಹಿಯರ್ ಇನ್ ಕೇಸ್ ಆಫ್ ಸ್ಪೇಸಿಂಗ್ ವಿ ಶಲ್ ಗೋ ಫಾರ್ ದಿ ಪ್ರೀವಿಯಸ್ ವ್ಯಾಲ್ಯೂ ಅಥವಾ ಲೆಸ್ಸರ್ ವ್ಯಾಲ್ಯೂ ವಿ ಹ್ಯಾವ್ ಟು ಕನ್ಸಿಡರ್. ಸೊ 93.44 mm we shall consider it as 90 mm center to center. If we had considered 25 mm, we would get the spacing as 180 mm or 200 mm like that. So here in this case, just to illustrate some, there is nothing wrong in choosing the diameters of the bar, but what we need to concentrate is the availability of the material. If in case you are designing in a field, there will be some standards for using the reinforcement in the foundation. So in that cases, you can consider whichever the type of members which is available in the site. So here in this case, I have just considered 16 mm dia. So provide 16 mm dia bars at 180 mm center to center over top face. Since this is hogging bending moment, so hogging bending moment ಅಂದ್ರೆ ಏನಾದ್ರೆ actually the bending moment should be indicated. So if I draw the elastic curve of the diagram, see your elastic curve would look like this. See, these two are the column loads. So your elastic curve would look like this. See, elastic curve. See, elastic curve. So your elastic curve would look like this. So at the center, which is what we have taken the maximum bending moment. So here, uh, it is hogging in nature. So whenever there is a tension, so at the central portion, the tension reinforcement should be provided at the top. So at the column phases, you have to provide the reinforcement, that is main reinforcement at the bottom. So this is what the basic considerations are. At the tension side, we will provide the what reinforcements. So here, after providing 16 mm diapers at 90 mm center center, actual AST provided is what we have to calculate. So again, same formula, spacing formula, area of one bar divided by area required into 1800. Instead of area required, you put this 90 mm, that is the spacing. So you will be getting the area provided. So 4021.24 mm square, which is what the area what we have provided. So this is the reinforcement what we will be providing for MX. So we shall see the diagrams later. Okay, so we shall consider and calculate the area of steel for under column A as well as under column B. So under column A, the bending moment was MA is equal to 79 kilonewton meter. So what we require is ultimate moment, that is factored moment. I will multiply this value by 1.5, so we will get 118.5 into 10 power 6 Newton m. Again, substituting in that modified AST formula, I will get the value of AST as 560.81 mm square. See here, the value of AST is very less. See here, 1000 ಇಂತ ತುಂಬಾ 6 mm diameter ಎಲ್ಲ ಏನು ಫೌಂಡೇಶನ್ ಯೂಸ್ ಮಾಡೋದಕ್ಕೆ ಆಗಲ್ಲ. So there is one requirement according to state design, that is minimum area of steel to be provided. So the minimum area of steel for any cross section is 0.12%. So 0.12% of the gross cross-sectional area, that is B into D. B is width and D is depth. So depth according to this formula, 0.12 divided by 100 into 1800 into 660. 660 is overall depth. So here overall depth what we have considered. So the AST minimum, that is the minimum possible AST what we have to provide is 1425.6 mm square. But according to this formula, according to the moment, we have 560, which is very less. So we have to provide this value there, which is 1425.6 mm square. So when I consider this as AST, I shall consider the diameter of the bar. See here, I will now apply the thumb rule. since the value is between 1000 and 2000, I shall choose the values of the diameter of the bar within 10 and 20. So 10 and 20, with this value is very close to 12 mm. So since it is very close to 12 mm, and I should consider 12 mm dia bar. So same formula, area of one bar divided by area required multiplied by width of the foundation. Uh, I will get 142.8, so we shall provide 140 mm as the spacing. Therefore, provide 12 mm diabars at 140 mm center to center. So the actual steel provided is again the same formula, width into area of one bar divided by spacing is the formula. So AST provided will get 1454.11 mm square. So this is how we have to calculate the longitudinal reinforcement under column A. So here there are again the longitudinal reinforcement under column B. We shall consider the moment under column B. So the moment under column B according to the bending moment diagram 389.7 kN/meter. So I will convert that to factored moment by multiplying it by 1.5. So I will get 584.55 into 10 power 6 Newton mm. So I will substitute the same again the modified EST formula. When I substitute it, you should be very careful with substitution. So the answer what I have got is 2899.97 square. Since the value of AST is between 2000 and 3000, I can select the diameter of the bar anything between 20 mm 25 mm. I like that, not more than that. ಜಾಸ್ತಿ ವ್ಯಾಲಿಗೆ ಹೋಗಬಾರ್ದು ಕಡಿಮೆ ಬರೋದು ಸೊ ಐ ಆಮ್ ಜಸ್ಟ್ ಕನ್ಸಿಡರಿಂಗ್ 20 mm diabars, so spacing pi d square by 4 divided by actual area required into width of the foundation 1800. So I will get 194.99 say 190 mm. So provide 20 mm diabars at 190 mm center center. So AST provided is equal to 2976.25 mm square. So this is the this is what we have, which is the area of steel area provided what we have to calculate. So after calculating all these things, we have next we have to check for shear reinforcement. So shear, previously in the previous steps we have already calculated the punching shear parameter. So punching shear we can also say it as two-way shear. Uh, Whereas regular shear force what we can call it as a one-way shear. So we have to calculate the one-way shear and two-way shear. So one-way shear we have to calculate, that is a shear check what we used to perform while doing the beam problems. Now what we shall do is we have already double shear, that is two-way shear, punching shear value. So according to the punching shear, we have already provided some reinforcements. So for the same one-way shear, we have to provide the reinforcement. If the parameters are in within the safe permissible limits, then we shall provide just nominal uh, reinforcements. Okay, so here you can also observe that the spacing is within 300 mm. So the spacing should not be more than 300 mm. If I had selected 25 mm, I would get 320 mm. So I had selected 20 mm. So we should be very careful while selecting the values. See here. So we shall just revise the things what we have done here. According to the calculation of steel, so we have to calculate the longitudinal reinforcement and transverse reinforcement. So today I have calculated the transverse reinforcement. So the bending moment diagram. So according to the bending diagram, the center of the span we have 1x value. So for mx I have calculated the steel. For ma I have calculated the steel, and mb I have calculated the steel. So this is 1x is 510 and ma is 71 and d is 389.7. So we have a formula according to IS 456, MA formula 0.875 ST. This formula. According to this, we have also this is not given in any code book. This is just a modified EST formula to make the calculation very easy. Substitute the value. One thing you should not you should keep in mind is you should always multiply this value of moment by 1.5. If you don't multiply the value with 1.5, then that value will become wrong. Okay. So what you need to do is you have to multiply the moment value by 1.5 so that we have factored value. Factored value. What we have is the CST having spacing and selection of the diameter of bar and spacing and the actual row. Then consider TA, substitute the values, get the steel parameters. Here, I have calculated EST minimum here. So EST minimum is 0.12% of gross sectional area. Since I have calculated once, the minimum requirement is 1425.6. So here, according to this formula, I have got 560. So I will be considering the minimum steel value. In the previous case, whereas MXL what we have is the area is more than 1400, so I kept quite there. So while considering column B, here also it is the value of PST is more than 1400. So here also I have considered this value only. Whereas in this case, the value of EST is less than 1425. So I have to consider 1425, which is the minimum reinforcement requirement according to IS 456. Okay, so this is a limit state design for your longitudinal reinforcement calculations. In the next class, we will be calculating the transverse reinforcement. So we should consider the transverse reinforcement in the next class. So many of you have joined just now. There is no problem, but anyhow, you had to join this class now, Vilas sir class now. So in that time itself, I have started my class. So there is no need for you to inform earlier. Okay. So hope you're understanding the problem. I'm taking step by step. I'm not forcing you to sit for longer time and listen for longer answers because uh, saying is very easy. And just teaching and explaining is very easy, but when you consider the what you call when you consider the practicing, you should be very careful in each steps. So step by step ನೆನ್ಪಿಟ್ಕೊಳ್ಬೇಕು. This is a lengthy problem. You have very lot of lengthy problems in this subject. So each and every step should be clear for you. Okay. So don't leave the class yet. I'm taking the attendance.